This next session is called Python, the Architect's Secret Weapon. This is going to be by Tadeh Hakopian. Please help me welcome Tadeh.
Thank you, everyone. We made it. All right. That's why you got to test your AV equipment ahead of time. Otherwise, you get unexpected results. But anyway, that's the deck. I'll give you a couple seconds there and we'll move on. Make sure we make it on time. But don't worry, you'll get this QR code and link at the very end again. Just want to give it to you ahead of time. Okay, a little bit about myself, Tadeh Hakopian, currently a program manager at Amazon. I connect information between physical building spaces and data. I have 12 years of experience in architecture and construction. Got into Python because I was tired of using desktop software to click through too many options, and it was taking forever. So Python helped me out with some automations. And I've been talking about data and modeling for a couple of years now. So this is kind of my perspective on how architects, designers, engineers, and builders in the construction space have used Python for the architecture projects. So it'll be kind of like an overview of the kind of solutions we see in that space. And we'll talk about scales, because architects love scales. We like logarithmic scales where we go from like, a 32nd inch plan to 16th to 8th to 4th to 1 foot, or 1 inch equals 1 foot. So we'll talk in the sense of scaling this up. So we'll start with scale 1, which is the building itself. And when people think of architects working, this is usually the picture, somebody standing at a desk with a drafting table, drawing away. It's very beautiful, very traditional. And architects still like to do that. They still like to be tactile with their hands. But this day and age, a lot of the work is actually done like this, in this kind of software called Building Information Modeling, BIM, B-I-M. You'll hear that word a few times. This is a software called Revit, popular in the space. And by making a 3D model, you can literally get as fine-grained as you want between the actual 3D space like that and all the drawings you need to produce a document. And this has been used for a long time. Most of the buildings that have been designed and built the last 20 or 30 years have been using software like this, not just CAD, but actual 3D modeling software. Because you can do things like model the entire site, like this house, and you can then kind of scale it back, draw sections, and those sections contribute to studying the building and giving you drawings from different angles and very sophisticated workflows. And that's great. So there is more you can do, but you kind of hit a limit to what the vanilla out-of-the-box tools go. So this is the first step of how does Python help architects, and this is kind of where I was kind of learning the curve for Python. There was all these tools built for software like what I just showed you. And we'll start with this example of how Python was like this entryway, a gateway into how we can solve problems in architecture, and we'll go from there. And we can have Python help us with modeling in 3 ways. I'll show you 3 examples. It's Revit Python shell with the Revit Python wrapper, which is one tool. It can let you create custom applications. PyRevit plus Revitron, which is another way of using Python applications on top of this Revit software. And then finally, Dynamo BIM, which is a low-code application using IronPython or CPython. So we'll check out a few examples. Revit Python shell uses IronPython. For the .NET framework, a lot of software built for the enterprise space is .NET based, so if you're not like a coder who knows SDKs like I was years ago, I wasn't really understanding any of that stuff. This is like a nice little interface, a wrapper around that. So you can access the API in the desktop software for modeling using just the IronPython interpretation. And it provides access to both the Python standard library and .NET framework. And there's tools like wrappers. So for example, here, you can create a tool, a script, that will let you do something that's kind of hard to do with out-of-the-box Revit, which is run a way to capture the bounding space of a model, which is handy if you don't want infinite space in the model. For more complex objects like this shape right here, that'd be kind of tricky, but with this script, you can run a code to do it for you, which is really convenient. It's a shortcut. However, some people running that might be a little too complicated, installing it, running the script. So this is where PyRevit, the next application, comes in handy. It's an add-in that has its own set of tools, but also lets you script your own tools for C# with Python, just like Revit Python shell. Comes with its own productivity tool set and a UI interface, so you can use it to create buttons, and includes instructions and guidance and a community around it to help you understand how to make your own Python scripts. And it's widely adopted. So for example, instead of running a script, you can make a little tool set made with Python code for the Revit application, and it can let you do cool stuff like match colors and color your building, which might not be that easy and convenient to do with the out-of-the-box tools. But for some people, this might still be a little too complicated, so this is where we have a Dynamo BIM, low-code scripting tool that comes with the Revit software itself, open source with enterprise support from Autodesk, and you can prototype your own tools, and you can also do 3D modeling solutions with this one. And it's a connection between the geometry and the data within the project model. And it just looks like this, like low-code applications everywhere. It's got the node and wire solution. In this case, we're just trying to make some coordinates X, Y, Z with some known points to create a shape. Very simple stuff. But it also has a Python script node that you can use to then generate your own scripting solutions. And in this case, what you can do is really optimize your code. And in this example, we're just importing the runtime library for the application, proto-geometry, Revit nodes, and then all we're saying is at a point 000, start from there, the internal position, and we create a for loop, X, Y, Z, starting with X, 0 to 100 feet, 20-foot increments, then Y, 0 to 100 feet, 20-foot increments, and then Z, again, 0 to 100 feet, 20-foot increments to get your X, Y, Z. And with that, we create something like this matrix of shapes we can populate very quickly with just that script. We don't have to click, 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 and make modeling elements and modify it. And from there, you can then write it to your model. This is a simple example, but you can see I can quickly populate a model, which is handy. But it can also let you do something that you can't do conventionally. In this example, all we're specifying here in this Python script is a width and length, and a origin and axis and a degree that lets you rotate. And you get this shape out of it, a rotating twisting tower, which would be very hard to do with the out-of-the-box tool set from the enterprise software. And you can go even further. There's Python, there's also more customized nodes, like this tool where you can use the curve mapper to create floors within a twisting tower that can curve based on that sine-cosine faction. So there's a lot of just easy to use out-of-the-box solutions for architects these days. And that's all through one software. That was an example of my starting point. But we'll move up a scale to the site. And for that, we need Blender. What Blender is, very fancy colors here. Blender is written in Python, C, C++ code with a lot of add-ins in Python, and has a ton of support for scripting integrations. People have used it for media, video games, rendering, animation, you name it. And you could also use it for designing buildings. But the fundamentals of Blender is using these cubes, which are meshes, that can mutate into shapes in just about any way you want, either through the UI or through scripting and coding tools. And that combined with another open source solution called Bonsai/Blender BIM, you can use these BIM solutions that have information and geometry into Blender, which itself is an open source solution outside the enterprise environment that something like Revit's built for. And you can make a writable format with parametric modeling through an open source solution. And you get results like this. Using those same cubes, you can use procedural modeling to then get shapes that resemble buildings, so you can actually refine it to the building with then windows and doors. You can slice it at a floor to get a floor plan. And from there, you could actually make real drawings, which is really great. So this is something you can do to really expand what you can model, because the traditional tools just think in terms of traditional drafting and modeling spaces. So this really lets you take it further, and you can even make an entire building or import one from another source. In this example of all these great studs you see in a house, you can visualize it all in Blender, and you can take it further and really adapt to different tools like the site analysis tools. It'll let you see the solar path. That arch over the building is every position the sun would be in at a given latitude of the year. So you can study the sun patterns to see if your building is casting shadows on plants or it's getting too much heat or cooling on a given side of the building. So you can really study the site here. And if you want to get really crazy, do something that you can't really do in these constraint softwares, you can create generative designs. This is a tower design, a hypothetical tower design, where they're twisting the tower and providing a facade and rendering all at the same time, which really expands your ability to design and create ideas. It's all through Blender and its environment. So you can really expand the solution set. And again, using different scripting solutions, low code, Python. But we can take it further and go to the neighborhood scale, next scale, 3x. You are all getting very sleepy. No, just kidding. So this idea is how do we really go from just buildings. Architects, because we touch buildings so much, we think in terms of buildings, but if you can do those examples I showed you before where you can make your own scripting solutions, whether it's that simple XYZ positioning and then you just rotate it, or create those site expansive ones, why couldn't you do something like come up with a prototyping solution? Same idea, but for an urban network. In this example, Studio KPF, an architecture studio that works on high rises, they took a matrix between residential, commercial, retail, industrial, civic, park, and say, okay, how do we generate different options for different urban environments? And because architects and urban developers and urban planners are really thinking in terms of how do we redevelop the entire city and not just a building. So you can see different permutations that they experimented with. But what's great about this is you could take it from here and say, okay, this is the layout based on these matrices and create a real mapping to a building environment. In this case, they're showing, okay, what if we were to just create that different mix and just rotate it and really use machine learning, data science to help us understand the urban environment and give us all these optioneering, what they call optioneering, to see what works best and visualize it, because everybody wants to see the results and see what does it look like, towers, low-rise, parks, what do we got here? But also score it and say, okay, certain variations have different benefits when it comes to density, views, analysis. That way they have something they could use data to back up their design. And that could be done at this larger scale. You could do it with towers. This is another example where you use it, the same concept of using different options and coming up with different scoring criteria for, does it make an efficient solution? Does it make a good value proposition? What's the daylighting? Does it block views? This is the kind of tools architects have been playing around with for a while, using machine learning and different algorithms that usually start with Python. But we can take it from there and go to the city format. So we talk about urban environment, it can go even bigger than the city. And with that, we have the data architecture for architecture, also called the city GML format. GML just means geographic markup language. And it's a format that helps with the conceptual model environment exchange for the representation storage of virtual 3D city models, because there are entire data sets where you can have the entire city and all the information mapped. So that's a big data issue. And what they do is let's put a schema here. Okay, well, we have information for terrain. We have information for hydrology and water, but we also have buildings. You ever seen those Google Earth views where everything's just buildings if you populate a building? That's also something challenging. How do you know what's the building? How do you know how big it is? So this is one schema for mapping it out. So you have the building itself, whether the building happens to be, whether it's a house or a high-rise, and it's then separated into interior rooms and interior and exterior bounding to create the interior concept of a room, which is a finite enclosed space, and the outer shell, which is the parameter that encloses it. And from there, you can then separate it into the internal wall surface, ceiling parameters, the external wall surface, and roof, so that you have a data format that captures that, and it's easier for you to manipulate that information at a finer grain level than just, here's a cube, and it looks like a building. So that's city GML, and that's more for urban planning and land. What we can also do is match it with the other data architecture, which is called IFC Industry Foundation Classes, which is a different hierarchical structure to represent buildings starting with project, including elements like sites, stories, various architectural and structural components. In this case, zooming into that site, here's a IFC, just a building room. It's like, what is the room? Room goes into the building floor, that floor goes into a story, that story goes into the building, so on. So in this case, we're specifying floor area, the function of the room, the height of the floor, the room name, the room number, the room volume, everything you would have associated with that room is as a parent-child relationship. then you can take the city GML knowledge graph, you could take the IFC knowledge graph, put it together as, in this example, a graph linking and compare the two data sets, because sometimes they're disparate. IFC is more from like a specific project site, whereas CityGML is more from like a GIS urban collection, and you can start linking these two sets and create architecture around it for what I call urban scale DevOps. In this case, this one example, we have all the land uses, terrains, water, buildings, and every attribute, then feeding into a CityGML model, including the IFC, which can then be fed into like an SQL database they can then use to create applications. Then you have the application layer on top of that through something like Cesium, and then you can apply that to end users who can then actually access all this data. And you get a result like this. This is the architecture they use for Helsinki, the capital of Finland, to combine all the buildings they have in their central district with all the terrain, hydrology, and information they have in the urban scale and map them together so they can do better urban studies, urban planning, and really understand the lay of the land. So that each of these buildings you see here actually has data telling you what this building is, what's the occupancy, how many people would access this building, so you can better understand the flow of traffic, people, where they're going, and help plan. So this is urban level, and what's cool about this is as long as you have these data sets, you can craft it. Helsinki, biggest city in Finland, but there's also a data set here, and this is New York City. This is something you can play with online. You can just go Cesium, New York City visualization. It has everything like this mapped out ready to go in your browser. And you can take this data, and what you have here is showing you every single building in New York City, and then use this kind of architecture where you can pair the city GML data like this with IFC, and then you can say, okay, this is the Empire State Building that has whatever, 70, 80 floors. This is what its use is, and really you have a database of the building environment behind it. So this is where you can go, where you have like these data models combined with the urban scale information. And you could also go underground. This is an example of using like LiDAR scans to have underground environments and really understand the underground subterranean like subways here, and actually see use cases, people using them and going back and forth. Which leads me to the next stage, which is 5x the data. And data is getting more important for building owners, developers, anybody who's touching a building. An example here, we have a retail environment. It's a couple 100,000 square feet, and you got the building, but everything in blue is a mechanical component. Most buildings, including this one, have huge dry handling units, air handling units, which control the airflow. So big that if you were to actually go to them, you could probably stand inside of them, and that's how you manage the environment inside of a building. And if you just show only the mechanical equipment in blue here, you see it's a substantial amount of equipment. That's a big ticket item for any building owner to manage. And going back to the building information modeling and management environment, you can actually create a type of pivot table from these 3D models and say, okay, this is every single piece of mechanical equipment, which is great, but it's stuck in this model. So what they do is they publish it to something like IBM's Maxwell solution for maintenance and operations. And you can see, okay, here's a list of all the components you could put into a database. So that's a data exchange, but it's still very manual. So they want to people want to like make it easier to create what they call a digital twin schema. Digital twin is just a virtual representation of a physical object. It's been used in aerospace for decades for satellites and aircraft that they, you can't actually go and, look at while they're operating. So you need remote sensing. So they're starting to do this for, physical assets. They're, buildings and equipment that aren't going to go anywhere. So what you do is you take all the information, you need an input, so that's documentation, drawings, 3D models, data from like spreadsheets, and even laser scans, point clouds of different buildings. And then you create a 3D model environment with information built into it, like this piece of equipment here, mechanical equipment. And then you can export that into different formats. You can have data validation reports, layouts, mapping for construction, eventually like an interface for how the equipment's operating with time sequence data, which is really cool, but it's getting kind of complicated to handle this much information. It's kind of a put together with duct tape more often than not. So what people are doing is using solutions like OpenUSD, which is US Universal Scene Description, which will take formats from Maya, Blender, Revit, AutoCAD, just about everything, and then use it to interface all of them into a consolidated format that shows geometry And this is something developed by Pixar, adopted by NVIDIA, and other companies like Adobe. So you can have an easier way to federate your models. And the beauty of it in the future here is you can use Python bindings for all this moving forward. So it's not just something you have to, again, duct tape together. It was based in C++. Now Python bindings are possible to do all this base imaging and mapping out. And here's an example of what's possible with that. Here's customers walking through a retail environment with camera tracking to figure out what they want to buy. And this is an example of the OpenUSD at work with the digital twin environment using cameras and AI to do tracking, just to see the use case here in action. So that's kind of like the future of buildings, data, and using tools from Python to really consolidate the data and the application layer. And moving forward, there'll be more of these applications now that people are getting more accustomed to the Python environment, the tooling of Python, talking about people in the build space, builders, architects are really starting to see the value, where you could take a model and put it through a process things through like NIMI, and then also apply something like volume space data, like a vector, and create a real workflow of data integration and collection. Whereas this was like the furthest things from most people's minds like 10 years ago, it started to become much more appreciated and adapted. So those are the 5 levels. We'll recap that real quick. We got the building level for authoring and working faster, that was 1x. We got the site level, 2x for collection of models and making more efficient sites and expanding beyond the confines of enterprise software. We have the neighborhood, that was generative designs and analytical studies of how to use data to back up your selection. We have cities, data architecture for architecture, urban scale DevOps, like we saw with those city GML and IFC formats. And then we got the data, the information, digital twins, which is the largest kind of scale. When you think about it over time, that's what you collect. Everything else prior to that would be relatively static, and data is streaming. With that, I have here some references and documentation for most of the tools we saw today. If you want to see more, there's tons of great projects out there for anybody who's curious about them. Dynamo, Grasshopper, all the Revit wrappers with Python, OpenUSD, you name it. And special thanks to the open source developers who work on these things. They make all these tools possible. The enterprise companies that produce the core software kind of support things here and there, but these are the real heroes who really make it possible. And of course, thanks to the Python community, because programming should be fun. Whoever gets the foot reference, if you know, you know. And thanks everyone for joining me here today at PyCon. I really appreciate it. It's fun having these talks, and it's fun sharing my perspective. Here's the QR code and the link if you guys want to capture everything I just said. This will be recorded and shared online eventually, but you can reach out to me if you have any questions. We have like 2 minutes for any questions, but we can talk down here. It depends on how you guys want to talk. So we only have a few minutes left, even though there's a break next. But anyway, thank you so much. Really appreciate it. I hope to see you around the next couple days.
You showed the 3D model with like the maintenance stuff inside the building. Do you ever take like heat maps of like where people travel in the building to look for as insight into like sort of management of the building for maintenance for the people who are kind of controlling and managing that building, or expanding that out to like the urban planning and like this is where the traffic is, this is where we need to place attention for like sewer storms and stuff like that?
Yeah, that's a use case you can apply there where it's like, okay, here's the activity levels. But it's only as good as your tracking. So sometimes the tracking is like imperfect because it could just be like somebody telling like a survey, oh, I went to this room based on like a spreadsheet, or it's based on like camera tracking data. So depending on how good the tracking is for the data, you can have a really good selection. I think traffic tracking in general for like our urban grid for driving, that's a good one. But when it comes to people, you need something to really capture that. Otherwise, you're gonna get like not great data. So and then that could be like a security camera or something like that. Those tend to be, but then it's hard to get that data out from like a third-party vendor or so forth. But in any case, assuming you have good data, you could implement that as well. They worked on projects where they use cameras to track equipment that moves and monitor that. So that's something important to the projects to see how, like, moving equipment that needs to be studied to make sure it doesn't fault is, behaving. So that's one way of using that kind of, in a sense, a heat map of moving equipment. So it's totally possible. It's just not quite of an evolution for inside a building because of the way you would have to actually track it, that it becomes useful. That's something that people are looking into. The camera example where people walking around, that was all based on specific cameras tracking people with AI, and that's, for example, Amazon. If you ever went to the Amazon Go stores, where you can just go in and grab things, it's a similar technology. So if you're set up for it, it works. Otherwise, it's it's hit or miss.
We got one more question.
Sure.
Hi, yes, you mentioned USD as a way to convert all these types of files into more universal ones. For one of my use cases, I would like to convert like PCB files. I use Altium or like Eagle. But those file conventions aren't typically standard, so is that something that we can add more file cases with like open source development, or is that fairly proprietary and it's more of a tool to connect other use cases?
It's OpenUSD, so it's open source. Okay. Yeah, I think there was a closed USD and now it's OpenUSD. So it's meant to be like, what happened was all these different softwares that did like 3D modeling, they all had their proprietary format. That example I showed you in the very beginning with the house, it's REVIT or .RVT for Revit, totally closed off. You really can't touch it. So that every company, Maya and whatever else has proprietary data files, will do that. For like decades, nobody cared until they're like, oh, we need to actually put these together in a federated environment. So Pixar pioneered this idea of, well, we just use something called universal screen description that would, make it easier to share this 3D information across formats. So it should work with most formats. There's documentation online to explain it. I think it's more about the building scale, but I don't see why you couldn't, adopt just about anything, because it's not meant to be GIS or, media environment or anything else. It's just meant to be like, geometry, scene description, so you can do massive scale kind of VR environments. Is kind of like one of the end goals of OpenUSD. So I'm pretty sure the application would work.
Okay, let's give Tadeh one final round of applause.
Thank you.